Okay, here we are, ladies and gentlemen. We've begun some topics of interest from chapter 13, sequences. We spent some time on general sequences. That was part one video. We spent some time on arithmetic sequences, which, just to remind you, generally start out with a given term A, and we add a constant D, or subtract the constant D to each subsequent term, and that is a arithmetic sequence because we're adding. Geometric sequence, aka geometric progression, is a sequence of numbers in which each term after the first is obtained by multiplying, not adding, multiplying the previous term by a fixed number. The constant multiplier is called the common ratio. So let's look at some examples. Now, I'm working this off of the sequence PDF, which is on Blackboard, and there's a sequence notes plus, which has some annotations in it, and there also are selected solutions from here, which is pretty much what I'll be dealing with, and we'll see how this goes. And there are some collections of problems which you should find interesting. And let's get going. Okay, let's start out with find the common ratio. Now, in arithmetic sequences, this is called the common difference. In geometric sequences, since we're doing a multiplication to get subsequent terms, this is called a common ratio. So just looking at the examples here, 2, 6, 18, 54, common ratio is clearly 3. To go from this term to the next, and multiply by 3, multiply by 3, multiply by 3. Okay, cool. Second example, dividing by 2, but definition is it's where we multiply by, so the common ratio is a half. Half of 100 is 50, half of 50 is 25, half of 25 is 12 and a half, half of 12 and a half is 6 and a quarter. Common ratio is 1/2. Okay, let's do another one. To go from the first term to the next term, multiply by -2, multiply by -2, -2 times -2 is +4, so the signs can alternate. Times -2 is -8, so forth. Common ratio is -2. Next example, to go from 4 to 7, well, 7 to 10, 10 to 13, 13 to 16, it appears that in order to get those terms, I'm adding. So this is not a geometric series. This would be, as far as we can see, an arithmetic progression or an arithmetic sequence, but not a geometric one. So, as usual, the rules and the procedures which we're looking at don't always apply, depends on the situation. So, formula for the nth term of a geometric progression or a geometric sequence is the nth term, which I can symbolize by L for the last term, or A sub n, is clearly A times this common ratio R times n minus 1. So in other words, to go from the first term to the next term to the second term, I multiply by 1 copy of R. To go from the second term to the third term, it's AR squared. So in the same way that we were counting in arithmetic progression, to go from the first to the second to third, the exponent is n minus 1 in this case. Okay? So let's look at some examples. And the first example that I'd like to look at is finding a given term in a geometric progression. Find the 8th term in the GP 3, 6, 12, 24. Well, two ways of doing this. One way of doing this is simply to, well, let's take a look at it. To go from 3 to 6, I add 3. But then when I realize 6 and 3 is not 12, I know it's not arithmetic, so I say, all right, what else could it be? Well, to go from 3 to 6, I could multiply by 2, and I say, well, geez, that What takes me from 6 to 12? And yes, it is. And from 12 to 24? Yes, it is. So this is clearly a geometric progression where the common ratio is 2, multiplying subsequent terms by 2 to get the next term. And I'm starting with a 3. So let's take a look over here at the selected solutions. Okay? And the rule is a times r to the n minus 1. R is 2, that's a common ratio. A is the first term, as we can see, is a 3. And to go from the first term to the second term, I multiply by 1 copy of 2. To get to the third term, I'm actually multiplying the first term by 2 copies of 2. So since I'm starting with the first term, that's why the exponent here is an n minus 1. Okay? So to get to the 8th term, I'm actually going to start with the first term and multiply by 7 copies of 2. So 3 times 2 to the 7th. 2 to the 7th is 128. 3 times 128 is 384. Okay. So that's how the process works. And you see this idea of the n minus 1 also in the arithmetic progression where we add n minus 1 common differences. Here, we're raising our common ratio, r, to the n minus 1 power because we're beginning with the first term. Okay? Okay, so let's do an example. You can do number 2 for yourself. The solutions are on Blackboard. Okay? But the idea here is we're talking about depreciation of a car. So it says a new car costs $20,000. Like, I wish, right? It depreciates. Depreciates means it loses value. 10% of its value each year. What's the common ratio? Well, you might think it's 10%, but it's really not. If it loses 10%, now just use some common sense. You start with a original cost, which we're going to think of as 100%. If it loses 10%, it means it's now worth 90% of what it was. So the R, the common ratio, is 0.9, which corresponds to 90%. So in other words, looking at our select solutions here, when you have the new car, it's worth 20,000. Okay, 90% of that is 18,000. So a year later, it's worth 18,000. It loses 10%. So 10% of 20,000 is 2,000. That's how we get the 18,000 figure. But the common ratio is 0.9 or 90%. 90% of here is, well, what's 0.9 times 18,000? 16,200. So this is when it's new, the end of the first year, the end of the second year, then it's only worth 16,200 and so forth and so on, and that's important. Okay, so the common ratio is 0.9, which corresponds to 90%. The original value is 20,000, which is A, and we're looking for n equals 4. So we have to carry this out for 1, 2, 3, 4 iterations, it's called. And you can do it, you can take 90% of this and figure it out, and that would be 14,580. Or you could take 10% of this, which is 1620, and subtract from 16,200, get 14,580. Either way, but what we're doing here is using the formula for the nth term of a geometric progression. So for the fourth term, I should really have I had a 4 here. So for the fourth term, I get 0.9 to the third power because I only use one copy of 0.9 to get to here, a second copy to get to the third term, and a third copy to get to the fourth term. So that's why it's n minus 1. It always trails by 1. And I should have really had an n here, so you might want to correct that. So if I work this out on my calculator, 14,580, and if I work this out using common sense, I get my 1620, and 10% of that is, I get 16,200. 10% that's 1620. Subtract, I get the same result. Okay, so a couple examples that have worked out. Now let's move on. We now know how to find the nth term of a geometric progression. Now let's find the sum. And this looks kind of messy. I mean, look at this. The sum of the first n terms of a geometric progression is this expression. You can factor out the a at the top, and this is an alternate way of writing it, where s sub n is the sum of the first n terms, a is the first term, r is the common ratio, n is the number of terms to be summed. Okay, so it's kind of complicated, so let's do a proof. And I think I have the proof written here. Yes, I do. Okay, so let's go over here. And I wrote it out in, shorthand here as well. So these are identical. I'm going to look at the typed up version. That's a little bit neater. Okay, so sum of the terms of a geometric progression. S sub n, meaning it's the sum of the first n terms. So I simply write them out. A is how much I started with. A times r would be the next term, ar squared, ar to the cubed, and the nth term is actually ar to the n minus 1, which is the formula that we've been dealing with all along. Okay, so if we go back here, okay, this is the formula here. The last term, in this case the nth term, is ar to the n minus 1, and okay, so that's how I get this. Now the trick is I want to solve for s sub n. Now this looks pretty nasty, so the idea is I multiply every term by r. So r times s sub n. You might say, well, why would you do that? Well, all I can tell you is watch. If I multiply each of these guys by r, all I'm doing is I'm bumping up the exponent on the r by 1. So this is r to the 0. I bump it up by 1, I get ar. I multiply this by r, I get ar squared. This by r, ar to the third, so forth and so on. This one, I get ar to the n minus 1, and this term, I get ar to the n. Now, if you take a look at what I wrote down, many of these terms are in common. These are in common, these are in common, these are in common, dot, dot, dot. These are in common, these are in common. The only terms that are not in common are the last one and the first one. So what I do to simplify things, I do a subtraction. So on the left side, I get s sub n, meaning the sum of the first n terms, minus r times s sub n. And over here, all of these guys cancel out, because when you do a subtraction, anything minus itself is 0. I get a minus ar to the n. And then what I'm going to do is I'm going to try and simplify this. So I look over here, and since I'm solving for s sub n, I factor out s sub n. I get 1 minus r here. That's a GCF, right, factoring. And divide both sides by 1 minus r, and I get our common expression. Okay? Notice that over here, I factored out the a, which is fine. Okay? So now, here's the deal. If we're taking the infinite sum, the claim is n approaches infinity. And you're going to learn in Calc 2, we're going to prove this in Calc 2, that if you have a number raised to an infinite power, like right here, it tends to 0 provided r is between -1 and 1. So this term goes to 0, I get a 1 on top, I get a over 1 minus r. So a over 1 minus r is the sum if you're adding up an infinite number of terms, provided r is between 1 and -1. So what that means in English is if r is a half or a third or 2/3 or 5/6 or -1/2 or -1/3 or -9/10, all those are between 1 and -1. So if you take powers of those, you could try this on your calculator. If you take a number that's less than 1 in absolute value and keep on raising it to powers, since the bottom of the fraction is bigger than the top, it's going to approach 0. So that's the situation. So this formula right here is true for a finite number n, and this is only true if n is infinite, provided r is between 1 and -1. So let's see how that works in real life. Okay, so let's do some examples. So we're going to pick, let's see, what am I picking here? Let's see, I think I am picking. Okay, here we go. Examples. Find the sum of the terms in a GP geometric progression. Find the sum of the first 8 terms of the geometric progression. Okay, so let's actually do that. So let's find our selected solutions here. Okay. Now, one way of attacking this problem right here is to write out a bunch of terms. So if we did that, let's say we're over here. You get 2 plus a half plus a quarter plus an eighth plus a 16th plus a 32nd plus a 64. Those are the first 8 terms. And now since the LCD is 64, you can do that. An algebra student can probably do that with a little bit of help, and if you're not too nervous about things. And well, we could do that on a chalkboard, but that's not available. So at any rate, here's our formula. This does it for us, right? So if we're adding up, if the LCD is 64ths, this is 128 over 64. This is 64 over 64. This is 32 over 64. 16 over 64. An eighth is 8 over 64. Its 32nd would be 2 over 64 and 1 over 64. If you add those up, you're going to get 255 over 64, or 3 and 63/64. So in other words, almost 4. Now, you don't have to do that. You got a formula here. Okay, here's your formula for the sum of the first n terms of a geometric progression, and it's geometric because the common ratio is constant, so 1/2. And put in A is 2, R is a half, and this is an n here now, right? Look at that formula. Right, this is an n. So 1/2. Oops, sorry, what did I do? So 1/2 to the 8th, and 1 minus r is 1 minus a half. Okay, 1 minus a half is 1, so that means invert multiply, you're going to multiply by 2. That's how we get the 4 here later on. And this is going to be, well, 1/2 to the 8th power. And 2 to the 8th is, let's see, it'd be 256. So 1 minus 256. So 256 minus 1 over 256 over 256 minus 1 over 256 is 255 over 256 times 4. Get a little bit of canceling action here. That becomes a 64. You get 3 and 63/64. I highly recommend that you actually write out these terms. We're missing an eighth, a 16th, a 32nd, and you write those out. LCD is 64, and verify to yourself, to make yourself feel that this formula is credible. You will get this result. Okay? So sometimes a little tricky to have faith in these formulas, but I recommend that you do that, or else you're going to be a little bit lost. Okay, well, let's look at a classic problem. Oh, first off, let's do the infinite sum. Okay, now you add 2 and a half and a quarter and an eighth and a 16th and a 64th and a 128th and so forth. If you total these up as we go along, it's called partial sums, which you'll learn in Calc 2. 2 and 1 is 3. Then you add the halves, 3 and a half. You add a quarter, 3 and 3/4. You add a eighth, 3 and 7/8. You add a 16th, 3 and 15/16. You can pretty much convince yourself this is going to come out to be a 4. So let's use our little formula here. And this only is true if you have an infinite geometric progression, you're looking for a sum, and if the ratio is between 1 and -1. Well, here the common ratio r is a half, so that satisfies that. So the rule says a over 1 minus r. So a is a 2, 1 minus r is 1 minus a half. 1 minus a half is a half. 2 divided by a half, invert multiply is 4. Okay, let's do a classic. The bouncing rubber ball. Alright, this is a classic. A rubber ball is dropped from the top of a 90-foot tower. The ball hits the ground and rebounds to a height 2/3 of the height from which it was dropped. So when I was a kid, or well, my kids were little anyway, we had something called a Super Ball, and it was advertised that would bounce very high. It was made of this really hard compressed rubber compound, and in fact it did. It was a lot of fun. And in this case, we have a ball that is compressed to the point that it has a resiliency, or I'm not sure what you'd call it, that however high it was dropped from, it'll bounce 2/3 of that height. So let's pretend you drop it from a 90-foot tower. Now I understand a 90-foot tower is vertical, so I'm sort of like stretching it out to help us here. And here's what's going to happen. It's going to start at a 90-foot tower, drop down 90 feet. And then it says, because of the composition of the ball, it's going to bounce up 2/3 of that amount. So 2/3 of 90 is 60. So it goes up 60. And of course it drops down 60. And it hits the ground, and 2/3 of 60 is 40. So up 40 and down 40. And then 2/3 of 40 up and 2/3 of 40 down, and so forth and so on, dot, dot, dot. So this is an infinite geometric progression. Perhaps you've learned in science or in physics class that there's no such thing as absolute rest. So a particle is always moving along because of its the molecules and the atoms are always moving. And this is sort of what this is talking about. So you get this picture. It drops down 90 once. Okay, whoops. And then up 60 and down 60, up 40 and down 40, up 2/3 of that and down 2/3 of that, and so forth and so on. So in other words, the 90 occurs once, and the 60 and the 40 and that and so forth occurs twice, right? Once up, once down, up, down. Okay, so I factor out a 2, and here's what I'm looking at. I got, this is a 60, right? I got the 90 once, and then 60 twice and 40 twice. So this is a 60, and this is a 40, because 2/3 of 60 is 40, and 2/3 of that is 80/3, so forth and so on. So we get actually a geometric progression here. It's clear to see that r is 2/3, and the first term is clearly 60, right? Because 2/3 of 90 is 60. So we get an infinite geometric progression. Okay? And we start out with 90, and we have 2 times what's going on here in the brackets. So the first term, a, it's a over 2 minus r, right? So a is 60, 1 minus 2/3. 1 minus 2/3 is 1/3. Invert and multiply, so this is a 180. So you get 90 plus 2 times 180. 2 times 180, order of operations is 360. So the ball, even though it never really comes to a stop, right? It looks like it is, but it's really vibrating. Okay, so the ball actually moves a total of 450 feet. Now, not across, of course. This is up and down motion. I'm just spreading it out here so you can get an idea of what we're talking about. Okay, so that ends geometric progressions, and series, of course, means the sum, so geometric series. And there are some problems which you may want to work on. Let me see if I can find them here for you. Okay, here's an interesting set of problems. If you want to practice, I did this in my MAT 101 class, so you got some problems here. You got an arena, you got the bouncing ball problem with some different numbers, and it turns out even that repeating decimals are actually the sum of an infinite geometric progression. So 0.777 forever and ever and ever is 0.7 plus 0.07 plus 0.007 plus 0.0007, And you can, you can go through this, and this is your first term. Clearly, you're multiplying by a tenth, so your R is 0.1. Clearly, it's in here, so you should be able to find a fractional equivalent for this, which is the result of an infinite geometric series, the sum of an infinite geometric progression. Okay, so if you want to do that, I mean, that's strictly up to you, but it is on, I'll make sure it's on Blackboard, and I even printed out the solutions for you. Look at that, the solutions are in red. Gee, what a guy. Okay, so that finishes up here our discussion about sequences, and we're going to probably do some probability and counting, permutations, combinations, and maybe some induction, and what is the nature of proof in the future. And I'm not sure if I'll give you any work to do on this, but it's something that will help you tremendously if you go into Calc 1 and Calc 2. Okay, so I hope you're well, and if I see you on campus in the future, say hello. Okay, be well.